I will begin with a word of prayer. Dear Father, we thank you for this day, and I pray that you'd bless this class, help us to understand a little bit about differential Galois theory as we look at it together, Lord. In your name I pray. Amen. Check this out. See, I know not to, I shouldn't breathe right in there just yet. All right, it's getting better. All right, so here we go. Definition. Let R be a, oh man, that is so bright. Let R, why didn't I should have brought my other laser. I may have to resort to a more traditional. Here we go. So let R be a commutative differential integral domain with 1. We'll use the usual abbreviation prime for the derivative. All right, and oh, look at this. Our curly bracket is the ring adjoin what? Y, yeah, Y and all of its differential consequences. But, oh, I guess it's, as he says, it's polynomials and variables y, y prime, and so forth. All right, so, I mean, formally speaking, there really is no relation between y prime and y prime at the level of this algebra. But that said, the way that the derivative works on these formal polynomials is a formal mockery of how differentiation works, right? Like the derivative of y prime is y prime and so forth. The derivative of y is y prime. So that allows us to extend the derivation on R to a derivation on R adjoin all the derivatives of y, just by that rule. So he says that makes R into a differential integral domain, and this is a ring of polynomials in differential indeterminate y. Was it a question? No? Yeah, go for it.
I'm just confused on like the derivative of y to the I.
Mm-hmm.
Isn't it, like, would it normally be the derivative that would be like I times y to the I minus 1 or something like that?
Oh, but this is not, it's not y to the power I, it's the ith derivative. So like, what is y prime prime? It's, yeah. Good question though. I mean, that, I think, is a good question. So, since R is an integral domain, let's see here. Likewise, one can define, if you have more than one indeterminate, you can take y1 and all of its derivatives and y2 and all of its derivatives, right? This gives us a, what's he call it? Well, I guess if R is an integral domain, then that's going to give you a differential integral domain, right? And if you denote it, look at this field of fractions, R Lingle, Y Ringle, then that would be a differential field, which includes y and all of its derivatives, at least formally, right? So as discussed in our other handout, the derivation on a differential ring can be extended to its field of fractions in a unique way using the quotient rule. I didn't actually prove that in depth, but it was, like I told you, it's a kind of picky proof involving partial fractions and so forth. It's really quite neat. But anyway, thus, this is a differential field, and it's called differential. You can think of it as the differential rational functions in y. All right. Let's see, what else do we have here? So if we have a differential field extension, we can write that. Oh, so then if E is a differential field extension, maybe it's possible to write it as the base field K with, derivatives of a certain number of variables adjoined, right? This would be sort of like some of our extensions were finite, right? Then they're algebraic. We could think about it as the base field with a certain number of algebraic elements adjoined. So kind of like that, right? But anyway, this would be the differential subalgebra that includes y1 through yn and its derivatives, right? So it may or may not be possible to find a set of y1 through yn which gives you all of E for a differential extension. Excuse me. So that's the differential subalgebra. This is the differential subfield rather, because it's the field of fractions built over that. Now, you guys have not had differential equations? You have? you two have, did you guys talk about the Wronskian? Yes, Dr. Skimbortis always talks about the Wronskian. He likes the Wronskian very much. But your Wronskian probably only had this and that. You did Wronskian for two things. But we can define the Wronskian for n things in differential equations. Let me take a break from Bill's handout here for just a second. Open. I say open. Let's see here. So these are my differential equations notes. Here's where I try to remember where I've So for example, in differential equations, one of the things you try to do is to solve, you try to solve the, oh man, son of a gun. Oh, come on, where's the problem? Stink. Trying to find the statement of the problem, you know? I think it was stated earlier in the section as a thing. So this is generically, I mean, this isn't much to see here, but generically speaking, this is the problem you're trying to solve, all right? But this L is actually something like an d to the n, an minus 1, d to the n minus 1, plus da da da, plus a2d squared, plus a1d, plus a0, where d is, well, it depends on what the the independent variable is, but if it's time, it would be d dt. So I summarize this by saying that L is a polynomial in the differentiation operator. And so that's the problem, the nth order problem, is to solve L of y equals to f, where f is the so-called inhomogeneous term, all right? And the general solution to this is given to you by something called variation of parameters. And I'll show you how that goes briefly. So variation of parameters says what you do is you form the solution, the particular solution, in other words, L of yp equals to f, by taking a linear combination of these y1 through yn's. Now, y1 through yn, these are in the kernel of L. They're solutions to the corresponding homogeneous problem. L of y equals to 0. L of y sub I is equal to 0. Now, the v's, v1, v2, dot vn, these are undetermined functions, so-called parameters, right? And so you vary the parameters. If you can find them, then that maybe there's enough flexibility in your choices of v1 through vn to construct the solution set. We learn techniques in Math 334 for calculating y1 through yn as the so-called fundamental solution set. So I'm showing this to you so you have some appreciation for what the Wronskian is. That's why I'm doing this, okay? And so to make this a solution, I differentiate it, all right? And that gives me that. And then I say, okay, well, let's make constraint 1 be that all of this is equal to 0. If I do that, it keeps me from getting higher order derivatives in the parameters. And then if I differentiate this again, yp prime gives me this, all right? And in order to keep myself from getting higher order derivatives in the parameters going on, I set these guys to 0. And that just leaves me these ones for yp prime prime. And then I differentiate again, and I keep setting the terms with derivatives in the parameters to 0. Now, I mean, this would be sort of like, you know, these are constraints we're adding to the problem. It may or may not be reasonable when you make such constraints to a problem. You know, are you going to leave yourself enough flexibility to find an answer when you're constraining your guess so strongly at each step, you know? I always give the analogy of dating, you know. if you're looking for a mate and you put too many constraints on it, you may find that there's no solution. You have to. I mean, maybe wanting them to like Star Wars and Star Trek is too much. Maybe you just have to settle for just Star Wars. No, it's just Star Trek. I don't know, whatever it is, but you pick your favorite silly idea to impose on your future life mate. But anyway, so you keep doing this, and eventually you plug the solution into the differential equation, which has, we have to eventually obtain that forcing term f by plugging in yp prime prime, well, yp prime, yp prime prime, yp prime prime, prime, and so forth, and this happens. But actually it's not that bad. When you impose everything that you have, you finally find your way back to this formula here, and if you could see up above, it was equal to a0, f over a0. So if you take that, which comes from the differential equation, plus the n-1 constraints that I've written down, and put them all together, it gives you this matrix equation that relates the derivatives of the parameters that you don't know and the given inhomogeneous term, and that's the leading coefficient of the differential operator defining your nth order problem. And then the beautiful thing is that this matrix, the determinant of that, is what we call the Wronskian of y1 through yn. Excuse me. The Wronskian. And it can be proved that if y1 through yn is a solution set, all right, if they're all solutions to the differential equation, if the determinant of this thing is non-zero at one point, its determinant is non-zero everywhere. This follows from something called Abel's formula. I'll show you. Oh, what have I done? So here's Abel or Abel's formula, and for n equals to, I put this on tests a lot of times into 334, prove this formula. You can, if you have y1 and y2 are solutions, if you take the exponential of the integral of the ratio of the first and 0th coefficients to the differential equation, then the Wronskian is given by the exponential of this integral. So that's either everywhere 0 or everywhere non-zero. That's why if we have, but you got to understand, linear independence and dependence of sets of functions is more subtle than that, right? It's possible to have two functions which everywhere, the thing with the functions is you can have a different linear dependence in different parts of the domain and have linearly independent functions, even though you can have the Wronskian be everywhere 0 for two functions and yet have the functions be linearly independent. The example of this is the Wronskian of, say, x and absolute value x. Well, x absolute value x, rather. Differentiate this, you get 1. Differentiate that, you get, well, so x absolute value of x is this. These are both parabolas. This is y equals x squared. This is y equals minus x squared. The derivative of this is actually, there's 2, is this. Because it goes like 2x over here, and it goes like minus 2x over there. So this function, x times absolute value of x, is differentiable, right? But the derivative is discontinuous. Well, excuse me, the derivative, the second derivative doesn't exist, right? This is not twice differentiable at the origin. And the thing about this is What does this give you? Is there 2 there? Am I wrong about that? Oh, I'm supposed to put an x squared here. I'm an idiot. X squared is what I want to look at. Right? Then this is what? So, but these 2 functions, y equals x squared and y equals x times the absolute value of x, they're not linearly dependent in the same way for all x, right? I can't write x squared is equal to k times x absolute value of x for all x. That's what would be required for those to be linearly dependent functions on the reals. The thing is that they're linearly dependent in a different way for negative versus positive, right? Like x squared is equal to minus x absolute value of x for negative x, and it's equal to plus x value of x for positive x. So the Wronskian of these 2 functions is identically 0, yet these functions are what? They're not linearly dependent. These are linearly independent functions. Unless I narrow the focus to just positive or just negative numbers, you know? So domain matters. This theorem then is very powerful because it says for a solution set, this can't happen. If I have a second order problem, second order differential equation, the Wronskian's non-zero at one point, it's non-zero everywhere. So solution sets is where Wronskians are really, really powerful. And I'll be done with my spiel here in just a second. You can also calculate the Wronskian for the nth order problem if you're willing to do the tensor arithmetic, like so. And it turns out that even for the nth order problem, the Wronskian still satisfies this differential equation, which you can separate and integrate. Abel's formula is general. It's not a second order thing, it's an nth order thing. And so the long and short of this is when we go back to the variation of parameters problem I was looking at a second ago here, where was it? You know, we worked our way to that matrix, right? Times, oh, where'd you go? Did I already pass it? Sorry, guys. This is Liam's fault. Yeah, this is all Liam's fault. Somehow. I can't see variation parameters right in front of me. Where? Oh, there it is. So the point that I was trying to get to is this is the matrix, right, of the fundamental solution set. The determinant of this is the Wronskian, and that means that that's non-zero since it's a solution set, and they're linearly independent. We're assuming that y1 through yn are linearly independent. That makes this an everywhere invertible matrix, and so you can solve for the parameters, and then you can integrate. That's the method that's variation of parameters. This is a completely general method. So that's, you know, anyway, I do not test past n equals 2 in differential equations because I don't need that trouble in my life. So with that background, hopefully this is a little bit less vague, like why would you talk about this? The Wronskian is central to the discussion of linear independence of solution sets, and so that's why it's part of the formal algebra machine that we're building here in differential Galois theory. Let R be a differential ring, y1 through yn be in R. Define the Wronskian as usual. Yeah. Okay. All right, so definition, let E be a differential field extension of a differential field K. We see that E over K is, can you guys tell me how to say that? Dang it. Picard-Vassau? So we shouldn't say Vessiet. Feels wrong. Vissoy? Let us say a PV extension if E... anyway, so it's a Picard-Vassau. This feels wrong. It's PV extension. PV extension if E has no new constants. Ooh, so the constants of E remember the constants were the kernel of the derivative operator, right? So the constants of e and k are the same. Oh, and, I think there's an and here, and there exists some L of y equal to this, right? So it's a polynomial in, well, it's, what is it? It's a linear combination of y and its derivatives, right? With coefficients where are the a0 through an minus 1? Yeah, I feel like they're probably in, oh, they're in k, right? That's what this notation means. They're in k, right? So it's, oh, and y1 through a yn, such that when you evaluate this at yi, you get 0. And the Wronskian is non-zero, so that means that they possess the algebra that is known for a solution set of linearly independent solutions. I mean, this is the algebraic core of what it means to have a fundamental solution set. That's what's in this definition. So what he says is, this means that L of y equals to 0 is an nth order homogeneous linear differential equation. We demand that y1 through yn is a fundamental solution set. I would say that that's what this definition says. if when you plug it into this pattern, it gives you 0, and it satisfies the Wronskian non-zero, that means that y1 through yn are solutions to the differential equation L of y equals to 0 in the natural interpretation here. Okay, so it's, all right, so one can show that the solution set of L of y equals 0 is n-dimensional over the constants of k. And this means that if C is the field of constants, so the complex numbers, the field of constants, then the solution set L of y equal to 0 is, the span over the complex numbers of y1 through yn. If you've had differential equations, you've seen this. Basically, the solution, so function space is infinite dimensional, right? But linear algebra, differential equations doesn't seem very infinite dimensional. It seems very finite dimensional. The Wronskian is the determinant of a square matrix. If function space is infinite dimensional, how are you getting away with taking Wronskians of finitely many things? How's that work? It's because the solution set to a differential equation is finite dimensional, right? The fundamental solution set has n things in it, and the solution space is really an n-dimensional vector space. If it's non-homogeneous, it's an affine translate of that, because the homogeneous solution lifts the solution space off the origin. I digress. Okay, so, oh, finally, if E is equal to the differential field generated by y1 through yn, then we say E is generated by this solution set. All right. Some analogies. So K adjoin so K with curly bracket y is the differential analog of polynomials. All right. So that's like polynomials. This is like the rational function. In other words, this is kind of like the field with x in it. This is the differential field with y in it, right? He says instead of a polynomial, we have a differential operator. So a polynomial in here gets replaced with a differential operator. And instead of having roots, a root is something you plug into the differential operator, makes it 0, right? A solution is something, into the polynomial you make it 0. A solution is something that you plug into the differential operator and get 0. Right, so, what's this? Instead of a splitting field E being generated by the roots of f of x, right, a la Galois theory, or Galois, I'm saying it wrong. I can never say it wrong. I'm sorry, I'll learn. We have the Picard, Visso. I don't know. I feel like it's just. I don't know either. We need more French students, I think. Oh well. Hmm. So we have that the PV extension E is generated by the solutions of that. That's the analog of a splitting field. Okay, so what this was equal to that, right? This is the field, the field with basis, well, generated by alpha if that's a 0 for this irreducible polynomial, right? We mod by that ideal. What's the analog in the differential world? We can build E as the sort of, k adjoin its derivatives mod I if I is the differential ideal generated by this differential operator and its derivatives. So, now that he hasn't quite explained yet, right? Maybe he will, maybe he won't. I don't know. We'll see. So, let's see, he says E extends k and has solution y plus I. Oh, he's saying that the differential extension idea, it also includes the usual extension idea as sort of the 0th case. If we just look at, the differential operator being something silly. Well, this, well, I'll shut up. Anyway, at this point, he says, you might anticipate that the PV extension of Ly over k is unique up to a differential isomorphism extending the identity on k. I wonder. Usually at the point when somebody says something like that, there's a follow-up, and it's not quite that, isn't there? But, well, anyway, here's the definition. E over k, a differential field extension, the Galois, differential Galois group of E over k is, what do we got here? Differential field automorphism of E, which means it's a differential homomorphism like we talked about last time, right? And it's also a bijection from the thing to itself. It's an automorphism. So it's an automorphism which not only preserves multiplication and addition, but also the derivative. It's differential automorphism. And, and because we're looking at the Galois, Galois group, it's also, what's this? It fixes the base field, right? This is just like our field fixing automorphisms. So we just have differential field fixing automorphisms for the differential Galois group. We call this the differential Galois group of the differential field extension E over k. So what is that? Why are people looking at differential Galois theory anyway? What would the motivation be for this? Why do we look at Galois theory? It's to understand better possible solutions to polynomial equations, right? In the same sense, differential Galois theory gives us insight into possible solutions to differential equations. So, although I don't think differential Galois theory is quite as well developed as Galois theory, I think there are unresolved questions in differential Galois theory which have been more resolved in the Galois theory. But let's go on here. So what's the deal? So since every differential ring homomorphism is also a plain old ring homomorphism, we get that the differential Galois group is actually a subgroup of the plain old Galois group E over k, thought of as a plain old field extension. Neat. So what's this mean? E over k is the PV extension of some linear differential equation. Then we will call gal E over k the Galois group of. So remember that this is analogous to f of x equal to 0. L of y is analogous to f of x, right? So if we had a splitting field for f of x, we call the splitting field the Galois extension of f of x. So we're saying that this is the Galois group of this differential operator in the same sense. Like it's the Galois. Let's see here. The differential field extension is the extension in which the differential operator factors in the sense of finding solutions. Yeah. Let's see here. So that one, proposition 6.21, proves that a PV extension like so, is algebraically closed. Oh, wait a minute, where the constants are algebraically closed. If that's the case, then there exists a set of polynomials, whoa, look at that, such that, yowzers. Oh my goodness. I don't know if I want to get in all this. Yowzers. What's going on here? What is this saying? Set of polynomials. So for every automorphism, for every differential field fixing automorphism in here, we can write this jth solution as a linear combination of the ith solutions, and big F of those constants is 0 for all f and s. Oh. I think that's a really complicated way of saying that the solutions are independent. I think this is a way of saying that if you have the image of yj under a differential field fixing automorphism is equal to a linear combination of the other solutions, then those have to essentially be 0. That's my intuition for it. That's all I got for you. I'm sorry, guys. Let's see here. What does this get us? Let's see here. So, well, I guess the real question is, we know, I mean, here's what this paragraph is grappling with is, what does a differential field fixing automorphism do to a solution, right? We know in Galois theory, if we take something in the Galois group, an automorphism, and we hit a root with that, what happens? We go to another root of the polynomial which we're splitting, right? Like roots go to roots under the regular automorphism. So I think what we'd hope is that solutions go to solutions under the differential automorphism. And I think that's all he's saying here, is if we take sigma of yj, we get this linear combination of yi's. And the thing about linear differential equations is the sum of solutions is a solution. You remember that, right? This has been, I hope, drilled in. But so that's, again, a solution. So we're, yeah. Anyway, this proposition tells us that the differential Galois group is the PV extension of a closed subgroup of GLNC. In other words, a differential Galois group is a particular kind of linear algebraic group. Did we define linear algebraic group? We did not. That is a graduate level topic. Maybe you'll learn about it sometime soon. It turns out that the dimension of the Galois group, the differential Galois group of E over k is equal to the transcendence degree of that. All right, so I know our time is almost up here, so I'll try to move it along. So this theorem, I mean, this example, I think is probably trying to explain what's meant by that sentence right here. Let's see here. So GL1, the GL1C is non-zero complex numbers. Invertible complex numbers are non-zero complex numbers because it's a field. And the closed subgroups of this group are finite, hence cyclic, or the whole group itself. Let's see here. So the Galois group of any first order differential equation must be a subgroup of GL1C, and so that means it's either finite and cyclic or it's all of non-zero C. And then I think what he's doing here is looking at a couple different differential operators and seeing how those different options are experienced. So if we have a equals to 0, I've forgotten where his a is coming from. It's here. So L of y is equal to y prime. Well, we know how to find that equal to 0 just gives us constants, right? And so, all right, fine. Well, what is that? I mean, so he says E over K is trivial in this case, because you already have the constants, I suppose. So in this case, the Galois group is trivial. On the other hand, if A is not equal to 0, then this has solution T integral of that. When A is not equal to 0, this is transcendental over K. So, all right. Theorem. So finally, we come to the fundamental theorem of differential Galois theory. If E over K is a Picard-Vaisseau PV extension, and G is the Galois group E over K, if we have C as the field of constants, and it's, K is algebraically closed, or I think E is algebraically closed, then this usual fixed field correspondence and its inversion, its opposite, is an inclusion reversing bijection, as we've seen, from the collection of closed subgroups of G to the set of intermediate differential fields of E over K. And moreover, if H is a closed normal subgroup of G, then this is a PV extension, and the quotient of the Galois group by, this is just that. The Galois group of the fixed field of H. And if F over K is PV, then the Galois group is a closed normal subgroup of G. So nothing really surprising here in terms of, it sounds just like our regular theorem, actually, with just a little bit more window dressing. So then he defines what it means for T to be integral over K or to be exponential integral over K, much like we talked about the elementary functions last time and being exponential or being, a logarithmic extension. And then he defines a tower of differential fields, and he talks about what's called a Liouville extension. And at each step, I think we talked about this last time, right? It's either algebraic, integral, or exponential. And so what's it take for a differential equation to be solvable? We say that the differential equation L of y equals 0 is solvable by a finite number of integrations if there exists some Liouville extension with E a differential subfield of L. So L of y equal to 0 is solvable if its solutions can be obtained after a finite number of integrations, exponentiations, and algebraic operations, right? So that's sort of describing differential equations which take elementary functions as their solutions, is the idea. Yes, my brother spent that Liouville wrong, but I can't complain. As I said before, this is free. So theorem, this is a little bit surprising. Algebraic groups, he says, it turns out that a given algebraic group, the connected component to the identity is a connected piece of the algebraic group which contains the identity. So this leads to the definition of an algebraic group being called virtually solvable if the connected component of the identity is solvable. So the solvability that's interesting, it's not for the whole group, it's for the connected component of the identity, it turns out. So that's a little bit of a twist. And so the theorem is Liouville extensions have virtually solvable differential Galois groups. Moreover, L of y equals 0 is solvable if and only if its differential Galois group is virtually solvable. I guess we're still left with the question of what does it take for our differential equation to have elementary solutions, right? Is that already it? Let's see here. I feel like there's one other theorem left to say. Yeah. So finally, I'm sorry I haven't gone through the examples and stuff, but I wasted your time showing you 334 stuff today because I'm an idiot. Anyway, so let C be algebraically closed and F rational functions in X with the derivative of X being set to 1. So that's kind of like the usual thing, right? And let E over F be an elementary extension and E over F a Picard-Vaisseau extension with E a subset of script E. Then the connected component of the identity of the Galois group is abelian? So he says in the example he worked out above, the Galois group was not an abelian group, and that meant that E over K is not a Canadian elementary extension, thus this integral is not elementary. So now he has reduced elementary, whether or not an integral is elementary. If you can see the integral is a solution to a to a differential operator whose Galois group is non-abelian, it's not an elementary function. Yep.
Does that mean that the second blank in the homework was abelian or solved?
Ah, good question. So what was the question in the homework? The trouble is I don't remember the precise statement. But we should be able to answer those questions easily now. Oh, I think the solution had the solution.
It had an answer.
Oh, it did?
Well, it did on other people's, like other students.
Oh, right. Let's see here. Let's see if we can answer it for ourselves now, though. Galois theory is to studying solutions of polynomial equations, as differential Galois theory is to studying solutions of differential equations. This you probably could have guessed without listening to me blather on for the last 90 minutes.
I had random people guess.
Oh, yeah?
Yes, they got it
Did
right.
they get it? Oh, good. If a differential equation has solutions which are formed from elementary functions, then its differential Galois group is?
I said abelian.
Abelian is correct. Yeah. And I don't know, to me that's a very satisfying conclusion to this story arc, is that an abelian Galois group means that going back to calculus 2, it's a nice thing. I personally find that deeply satisfying, even though I don't understand all of the particular machinery we went over. I mean, I know I could work it out. I know you could work it out if you had time. It's just a matter of, do you want to spend the time working it out, So anyway, that's end of story time for today.